Hi, this is the Unit 4 problem set and also the Unit 4 review for everything we did in Unit 4. Alright, so first I'm going to slowly go through this so you can get an idea of what it's like, and then we're going to start doing this. Okay, number 1. An isotope with mass number of 63 has 5 more neutrons than protons. So protons plus neutrons is equal to 63, and 5 more neutrons than protons. So neutron minus 5 equals protons, which means protons plus 5 is equal to neutrons. So instead of writing neutrons here, I can write protons plus 5, which means 2p is equal to 58. That means p is equal to 29. 29 protons on the periodic table is copper. So our element is copper because we found out that there's 29 protons. Okay, 2 isotopes. Now we're looking for the percent abundance. So we have 6.01513. Let's put that as x plus 6 plus 7. 0.01601 x minus 1 is equal to 6.9410. Okay, now subtract the x's. 6.01513 . Oh shoot, it's not x minus 1 here, it's 1 minus x. So I'm gonna change this and add x over here real quick. Minus 7.01601. That gives us negative 1.00088 x is equal to 6.9410 minus 7.1601. Negative 0.07501. Right, that gives us x is equal to 0.0749 times 100 equals 7.49%. 100 minus 7.49% is equal to 92.51. So one of them is 7.49% and the other one is 92.51%. It's asking for a higher abundance, so it's going to be 92.51%. Okay, so we're looking for average atomic mass, so we're just going to add everything together. We have 50 times 0.0435 plus 52 times 0.8379 plus 53 times 0.095 plus 54 times 0.0236, and that gives us 50.435 plus 52 times 0.8379 plus 53 times 0.095 plus 54 times 0.0236. That gives us 52.055. Okay, average atomic mass, we would run to 2 digits after the decimal point, so 52.06. And if we look on the periodic table for 52.06, we can see that chromium is 51.99, which is very close to 52.06. So we can tell that this is chromium. Write the 4 electron configuration for arsenic, AS. Okay, AS is number 33 on the periodic table, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Alright, now for orbital notation, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. And all the S gets 1 line, all the P gets 3 lines, and finally the D gets 5 lines. Alright, 2, 2, 1, 2, 3, 4, 5, 6, 1, 2, 6, 2, 10, and finally 4p3, 1, 2, 3, 1, 2, 3. Alright. Now fill the table with appropriate data. So first the mass goes on top, atomic number goes on the bottom. Bromine atomic number is 35, so 35 Br. The charge is neutral, so we don't write any charges. Atomic number 35. Is it 35? It's 35, right? Mass number is 81, as shown over here. Proton is an atomic number, and since it's neutral, protons equal electrons. Protons plus neutrons is equal to the number is equal to the mass. So 87 minus 35 is going to be, all right. So neutrons is 46, since 81 minus 35 is 46. Now next we have MO, number 42. Number 42 on the periodic table is molybdenum. MOLYBDENIUM. The mass is 100. Alright, 2 plus charge. That means there are two less protons. Alright, first let's write atomic number 42, mass number 100, protons 42. Now 2 plus means it got rid of 2 electrons. It lost 2 electrons, which made it more positive. That means you lose 2 electrons. That means you have 40. 100 minus 42 is 58. Right. Our next, mass number 131, charge of 1 minus, the electrons of 54. So first let's find protons using 54. 1 minus means there's an extra electron than proton, which makes it more negative. So proton will be 53. 53 on the periodic table is iodine. So this is iodine. The mass we figured is 131, and it's 131 over 53 iodine of 1 minus. And the atomic number for iodine is 53, and neutron is 131 minus 53, which gives us 78. Alright, next one, atomic number of 82. 82 on the periodic table is Pb, lead. Lead with a weight of, we're not sure, 133 neutrons. Atomic number protons is 82 as well. 82 neutral charge, which means 82 electrons. Mass number is 82 plus 132, which gives us 214. 214 go on top. The bottom is atomic number 82 Pb neutral charge, which means nothing. All right, next one we have 3 plus. That means there's 3 less electrons than protons, which makes it more positive. So it's going to be 76 protons. 76 protons, 192 minus 76 equals 116 neutrons. And now atomic number is 76 also. 76 on the periodic table is OS. OS-MIUM. The weight is 192. 192 go on top. 76 go on the bottom. OS go on the side with a charge of 3 plus. Okay, so here we have write the equation for alpha decay of francium. Francium, let's look for the weight. Table. Alright, francium is number 87 on the periodic table. So we're going to write the weight on top. The weight on top, 201. Francium is 87. Fr. And that makes, let's see, alpha decay. Alpha decay is 42He. 42He. So 201 minus 4 is 193. 87 minus 2 is 85. And 85 on the periodic table is AT. Alright, next. Oops. 137. There we go. Write the equation for beta decay for TH. Alright, it's 81 on the periodic table. So 182 over 81 TL makes beta decay 0, -1 electron plus 0 plus 0, 182 minus 0 is 182, 81 plus 1 is 82. 82 plus -1 is equal to 81, and 82 on the periodic table is PB. Alright, write the equation for neutron decay. Neutrons, so we have barium 13, B 13, 4 makes, let's see, neutron decay is 1, 0, N. And that makes plus 12, 4, which makes also barium, Be. There. What particle has the highest energy? Alpha, beta, or gamma? And as we learned, alpha has the smallest amount of energy and gamma has the largest, so it's gamma. Alright, an element has Z number and A number. Alright, so it's AZX. A number is 150. Z number is 62. What does the element be described? So 62 on the periodic table is SM. Spendium? Would you write SM over here? How many neutrons are in this? So the weight is 150 and the protons is 62. So 150 minus 62 is 88. And how many nucleons are in this nuclide? Basically, the total amount of particles in the nucleus, which is 150, because that's what makes up the nucleus. Now, identify an element who's also a member of a halogen family, whose 1- ion contains 54 electrons. So we're going to find a halogen, and plus 1 has equal to 54. So X plus 1 has equal to 54, which means 53. That means it has to have 50. The neutral atom has to have 53 protons and 53 electrons. And what has 53 protons? Iodine. Beta particles. Nope, this is alpha. This is are repelled by positively charged state. Nope. Are more penetrating in the X-rays. No, X-rays are gamma. Are high-speed electrons. That doesn't look too much. D. Are inner gas, noble gas form for tin. Tin is SN, I think. Tin is SN. Okay, number 50. Oh, it's pretty long. Alright, that's why I told us to use noble gas notation. Great. So go up one, go to the side, is KR. KR. 1, 2, 3, 4, 5. 5s2. 4d10. 5p2. Alright, noble gas configuration for neutral atom of tungsten. Tungsten is 74 with a W. Alright, so W, it will be, we'll go up one, it's going to be Xe. That's a noble gas. And if we look to the side, it's 6s2, 4f14, because it has to go all the way on the bottom, and come back up for 5d4. 1, 2, 3, 4, 5d4, yep. Now, write the noble gas notation for As3 minus. Alright, As, we just did it. It's going to be 33, so plus 3 is going to be Kr. So the noble gas notation will just be Kr. Now, which of the following has highest energy subshell? Subshell, so if we look at Te2 minus, alright, so it's going to be 5p4. So the highest energy will be 5p. Oh no, 2 minus 5p6, anyways. Now consider this electron configuration. What is the highest energy subshell? 5p. What is the chemical symbol? 5p4 is Te. Oh wow, we just did it. Alright, so this one's TE. All we have to do is look at the last one to figure out what it is. Now, what is the total number of subshells? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 subshells. How many orbitals? 1, 1, 3, 1, 3, 1, 5, 3, 1, 5, 2. No, this one still has 3. So 1 plus 1 plus 3 plus 1 plus 3 plus 1 plus 3, 5 plus 3 plus 1 plus 5 plus 3. And that gives us 27. Although this says 2p4, but we count the p as subshell as a whole, so we count 3. Now, what is the classification? 5p4 is going to be a non-metal. It's not a halogen. It's not a metal, so all 3 of these are gone, and it's not a halogen, so it's a halogen. We didn't really learn that in class yet, but now I know. Process of elimination. Based on the electron arrangement, the element will be paramagnetic. Paramagnetic means they are unpaired electrons, and there are indeed unpaired electrons, so it's going to be true. Based on the Z number, the element will be radioactive. Okay, so radioactivity usually occurs in like the last column, and after like, let's see, BI, I think. We didn't really talk about this in class, but it's probably not radioactive. Actually, I'm 100% sure it's not radioactive, because you need to have way more protons and atomic mass in order for it to be radioactive. Okay, and then we have number 25. What is the wavelength in nm of a radio frequency? Alright, let me grab my table. Wavelength and frequency. That means we have to use one of our formulas. Energy is equal to Alright, so in order to find wavelength, we need to find energy. And then this question asks for energy, so we can answer this one first. Now, energy is equal to that number, which is 6.6262 times 10 to the negative 34th times what we have over here, 8.95 times 10 to the 7th. Okay, so now we plug that into a calculator. 6.6262 e to the negative 34th times 8.95 e to the 7th. That gives us 5.93 times 10 to the negative 26 joules. Okay, now that we found energy, actually no, whoops, we don't even need energy to find the other one. So we're gonna use speed of light. 3.0 times 10 to the 8 meters per second is equal to frequency times wavelength, x. So just divide this side, just divide the speed of light. E to the 8th by 8.95 e to the 7th, and that should give us 3.35 meters. Because remember, speed of light is in meters, so we're gonna have to convert this into nanometers. 1 meter contains 1 million. No, 1 million is millimeter. 10 to the 9th. 10 to the 9th nanometer, which means it's basically 3.35 times 10 to the 9th nanometers. Now, if the energy required to move an electron is that much, what is the frequency? Okay. Alright, so 8.23 times 10 to the negative 19th is equal to 6.6262 times 10 to the negative 34th times x. So basically divide this number by this number, and that would be 8.23 e to the negative 19 divided by 6.6262 e to the negative 34th. That should give us 1.24 times 10 to the 15th Hz. What will the wavelength be? I'm going to have to use the other light formula. So 3.0 times 10 to the 8th meters per second is equal to 1.24 times 10 to the 15th hertz times the wavelength in meters. So divide this number, divide 3.0 times 10 to the 8 by 1.24. Let me do that real quick. 3.0 e to the 8th divided by 1.24 e to the 15th. That gives us 2.419 times 2.419 times 10 to the negative 7th meters. 1 meter contains 10 to the 9th nanometers times e to the 9th gives us 241, which runs up to 242 nanometers. Calculate the frequency of light emitted in hydrogen Bohr model. Negative round circle 4 to circle 1. That is 97. I already calculate frequency. Okay, so let me think. Frequency times wavelength is equal to, I found the wavelength already, 97 nanometers. 97 nanometers. Oh, I need to convert it to meters first. So 1 meter contains 10 to the 9th. So which means 97 divided by, that's 9.7. 9.7 times 10 to the negative 8th. That is nanometers times the frequency, which equals to 3.0 times 10 to the 8th. Now divide 3.0 e to the 8th power by 9.7 e to the negative 8th power. That gives us 3.09 times 10 to the 15th Hz. Now, which type of electromagnetic radiation is this light? Alright, so 3.9 times 10 to the 15th. No, 97 nanometers. 97 nanometers is UV light. What series does this belong in? As we learned, the first one is Lyman series. UV is Lyman. Now, compare this transition from N2 to N6. N6 to N2. N6 to N2, that is 410. Which transition produces the greatest frequency? So higher frequency equals higher energy. Okay, so the answer to both of these will be the same. And the lower we found the lower the wavelength, the higher the frequency. So the smaller the wavelength, the higher the frequency. That means 4 to 2 will be the answer to both of them. N equals 4, 2, N equals 2. So basically, this one is 92 nanometers in wavelength. This one is 400 nanometers in wavelength. 414, 410, I forgot. It doesn't matter. It's 400 something. But the smaller the frequency, no, the smaller the wavelength, the higher the frequency. And the higher the frequency, the higher the energy. That's why both of these will be the same. Now, what's the longest in wavelength? Longest in wavelength will be radio, because it has the biggest frequency. No, it has the smallest frequency, which is why it's longest in wavelength. What is the highest in frequency? X-ray. And what is highest in energy? Visible. No, also X-ray. High frequency equals high energy, which equals to low wavelength. What element is neutral? Okay. Alright, so I'm not sure why this is here, but it's not very important. This is what's important. 2 filled orbitals and 1 half-filled orbital. So 2 filled orbitals and 1 half-filled orbital. So what element contains this? 4p electron, 4p5. This is basically saying 4p5. 4p 1, 2, 1, 2, 3, 4, 4p5. That should be bromine, which means it's Br. Oops. The answer to this is Br. What do you call the electrons of an outermost energy? That is easy. Valence electrons. Valence electrons. What do you mean when an electron is excited? So yes, alright. An excited electron is basically when it has higher energy than ground state. Now, an electron that is the lowest energy possible level is a ground state. Alright, now how many electrons are in an orbital? How many electrons are in the following? A filled p orbital. P has 3 orbitals, each contains 2, so 6. A filled d sublevel. D contains 10, since D can hold 10 electrons. Second energy level when it's full. Second energy level contains 8. 8 electrons can be held in the second energy level. Now, a half-filled P sublevel. P can hold 6, so half will be 3. A half-filled D is 5. And D is 10, so half is that is 5. Now, there is an orbital with a label 3p that. What makes this orbital different from each of the following? Okay, so different letter means different shape, right? P, D, and all of them, P, D, S, P, each is a different shape. And 2py means 2py compared to 3py. A lower coefficient means lower energy level. Okay. Write the electron configuration for the following atoms and ions and circle the valence electrons. Alright. Na on the periodic table is 1s2, 2s2, 2p6, 3s1. This is a valence electron. Since the highest coefficient's power added together is a valence electron, and there's only 1 3 in this. That's why the 1 is it. Let's keep going with Cr. It has 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 3d4, and then elements in the d4 turns into d5, and it's also one valence electron. Now Ca2 plus. If I can find it. Alright, Ca. So it's 1s2, 2s2, 2p6, 3s2, and 3p6. Since it's 2 less electrons, that means it will have the same electron configuration with Ar, argon. 2 plus means minus, which means 2 electrons gets taken away, which makes it more positive. And the original Ca should be 4s2, but since 2 electrons are taken away, now you have 3p6, which means these two added together, 8 valence electrons. O is oxygen, number 8, plus 2 minus, which means there's 2 additional electrons, which means you have the same electron configuration with neon, and its electron configuration will be 1s2, 2s2, 2p6, 2p6, and 6 plus 2, 8 valence electrons. Now, write the orbital notation for the following atoms. S. So 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 3p4. So 1, 1, 1, 1, 2, 3, 1, 2, 3. Will be 1, 2, 1, 2, 3, 4, 5, 6, 1, 2, and 1, 2, 3, 4. Alright. Now Mn is if we can find it. Mn. Alright, 3d5. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. 1 1 1 1 1 2 3 1 2 3 1 2 3 4 5 2 1 2 3 4 5 6 1 2 1 2 4 5 6 1 2 1 2 3 4 5. There we go. Now, is Hund's rule going to be important when writing an electron configuration or drawing an orbital? Yes, it will be. When drawing them, you write them all out first, and then pair them if they are extra. So Hund's rule states that electrons do not pair it unless they have to. And when you're drawing them and when you're writing them, it's not important when you're writing electron configuration. All right. When you draw an orbital diagram, you write them out first, and then pair them if you have to. As you see over here, we have 3d5, and I do not pair the 5 unless I have to, unless I have extra ones. So that's Hund's rule. And now it's not going to be important when you're writing the electron configuration because it doesn't matter. 1s2, 2s2, you don't see how it's really paired. How it has to pair like this first. All right, now our last question over here is this important when you have electron configuration orbital diagram? All right, this thing basically states that you have to go from the lowest energy levels first, from 1s2 to 2s2 and 2p6, etc. And that's always important, both, because you have to go from the lowest energy levels first, always. There's no other exception from that. No matter if you're drawing it or you're writing it, you always go from 1s2, then you go to the p, and then 3, 4, etc. So this is basically all the review for Unit 4. If you have any questions, leave them in the comments, and thank you for watching.